Hi class. This week we are doing modeling, geometry, and polarity. This lecture is a little longer than my normal lab lectures because I'm trying to give you as much information as I can. Next week we're going to build upon this in lab. So this isn't going to go away. And next week also, next chapter in the book is also going to expand on it. This is something that's going to probably carry through. So it's in your best nature to really try to draw the Lewis structures out and so forth. I understand that you can easily look up most of what is going to be on this lab, but trust me when I tell you that that's not going to save you in the long run when eventually we go back in person and you're going to have to build upon this. It makes it a lot easier if you understand the concepts instead of just learning the answers. It'll carry you through for better on this, especially for next semester. The first part of the lab is pretty easy. You're given these pictures, and you have one that is an ionic compound, which is sodium chloride, and then you have three other compounds that are covalent. You have table sugar, which is sucrose, iodine crystals, and sulfur. And basically it's asking of you to record 2 or 3 physical properties that you see. So this is not difficult. I'm not looking for some elaborate answer. Doesn't even have to be in full sentences, honestly. Just give me what you, as long as it's understandable and I can read it, what you see here. What can you determine from these? If you're confused about what goes on with these, understand what ionic compounds are, what covalent compounds are. Covalent are nonmetals. That it should by itself tell you some information about that. I did put together some physical characteristics. Not all of these are going to be based on what you can see from these pictures, but it will give you an idea of some characteristics. It says ionic compounds, but if you look at the next one over here, it says covalent, and you can see the difference between these. Then it's going to ask you about the microscopic level. So I put it together a slide. If you see in this corner, this gives you the picture that you'll see. And then I found some other pictures that give you a better idea of what's happening. So you have a sodium ion that's surrounded by 6 chloride ions and a chloride ion that is surrounded by 6 sodium ions. This arrangement makes this a very stable structure. It takes a lot of energy to break this apart. And if you check bond energy to break this, it's really high compared to a lot of other compounds. So this is what you would kind of see on a microscopic level. Not difficult. This portion of the lab is pretty easy. Now we're going to get into Lewis structures. You may like Lewis structures, you may dislike Lewis structures, but trust me, when you start working on this, it makes life a lot easier for you when you can grasp how to do Lewis structures. And that only comes with practice. It's not going to be something that happens overnight. You will have to work on these over and over again in order to fully understand compounds. So Lewis structure shows how the valence electrons are distributed around the atoms in a molecule. Covalent bond, a molecular bond, is a chemical bond that involves the sharing of electron pairs between atoms. So here's an example of HCl. You have an H atom that has 1 valence electron and chloride that has 7. Hydrogen has an open spot and chloride has an open spot. So you move those 1 electrons from each and now they can share them and create a bond. We usually do a line that is representative of 2 electrons. It's easier than keep doing dots all over the place and it looks a lot cleaner so you can understand better. That's why in most pictures of compound structures, you don't even see the lone pairs. So normally you would just see HCl. You don't see the lone pairs that are there. They exist, but we don't normally write them out. So when you see something, do not assume that it doesn't have lone pairs on it. This is why I ask that you should be practicing Lewis structures, because then you will immediately know when you draw them and you don't see them elsewhere. They're there, you just don't see them. So the chloride will fill an octet and the hydrogen will fill a duet. And this makes this a very stable compound. It's sharing the electrons to come together. Also, chloride now has 3 lone pairs and 1 shared pair, which forms a covalent bond. In order to fill an octet, some elements can form double or triple bonds. So HCl here can only form a single bond because hydrogen can only form a single bond. It will never be in the center of a compound. It will always be on the outside because it can't form more than 1 bond. But this is 1 shared pair of electrons. Oxygen can handle a triple and a double bond. So in between here, in order to fill an octet, it has 4 shared electrons. So two pairs of electrons on here. And nitrogen can also form a triple bond, and it has 6 shared electrons in between. So we see them as bonds, but really there's 6 electrons there. So I took this straight from your book, and this is to give a better idea about these things. Identify the numbers of shared electrons and unshared electrons in a Lewis structure. A lot of times, lone pairs are never drawn, and you wouldn't know it by looking at the N2H4. So this is, again, while I'm saying you should definitely draw these out. Don't just take the pictures that you can find on internet as correct. Draw them out so you actually learn the concepts behind this. So if we look at the first one, this kind of looks like a diamond here, which I disagree with. They should have changed those color bonds to highlight the single bonds in the lone pair, but they didn't, but they still highlighted them out. So overall, this has 14 electrons, valence electrons, to share to create this bond. Has 2 sets of lone pairs, and total of electron pairs is 7. You count all pairs on this compound, including the lone pairs. So if you have 14 valence electrons divided by 2, you have 7 pairs. Pay attention to the terminology with LabFlow. They ask some questions in weird ways. So they might want to ask you what the valence electrons are. They might want to ask you the total pairs of electrons. Make sure you're understanding what they are asking. Same thing here. We have a triple bond between carbon and nitrogen. Carbon can also handle triple bonds and double bonds. It will never have a lone pair on it, not in this chemistry course. So if you have a lone pair on carbon, something's wrong. You need to move that around. You can see a lone pair on nitrogen, which can handle that, and then the hydrogen will never have more than 1 bond on it. So valence electrons, you have 10, and then you have 1 lone pair on the nitrogen, but we don't actually care about that when we're looking at trying to put Lewis structures together, when we're focusing on the central atoms. Yes, that lone pair needs to be there, but when you start out trying to put these together and you focus on the carbon, which is the central atom, that should take priority. Then you figure out where the lone pair goes after that. Don't try to put that on the carbon. And total of electron pairs is 5 pairs. Again, LabFlow will ask something in a weird way. Just make sure you're understanding what it's actually asking. Okay, so if you don't understand how to draw Lewis structures, I strongly suggest you see the tutorial that I put up about how I make Lewis structures. If that doesn't work for you, then focus on how the book does it. And if that doesn't work, there's other ways that people do things on here. But I'm going to jump ahead. I am not going to go over how I did this. I'm just going to write this out because I'm assuming at this point, and I'm also going to put it on the module, that you should definitely see how to write Lewis structures my way or get comfortable with the book before you see this lab lecture. So we have CO2. I'm going to draw a structure for it. So again, I'm going to write this out. This is what I have. So I have 1 carbon, 2 oxygen. Carbon has 4 valence electrons. Oxygen has 6, but we're timesing that by 2. So this gives me 16 valence electrons. Again, I'm just going to jump ahead. This is what I need or want. So again, we're going to copy this right over. And this is going to be 8. And this is going to be 2 times 8. This is 16. This is going to give us 24. So 24 minus 16 is going to give us 8. Remember, 2 electrons equal 1 bond. So I'm going to divide this. This is 2 electrons, 1 bond, if you needed to write it out. This is going to tell me I have 4 bonds in between this compound. So you have 2 oxygens and you have 2 carbons. Carbon is the least electronegative, and I'm going to cover that later. But it's also, you want to keep things as symmetrical as possible. So I'm going to put carbon in the middle and put an oxygen on both sides. I have 4 bonds I need to fill in. So 1, 2, 3, 4. Now I need to determine my valence electrons. So I am going to, this is symmetrical, keep it as symmetrical as possible. I'm pulling it out. 5. Determine the rest of them that you have to still add to this compound. So I have 16. I used 8. So let's subtract the 8. I have 8. So I have 8 valence electrons I need to surround this with. But carbon's already taken care of. I have 2, 4, 6, 8. So this is done. I do not have to put anything on an octet, worry about an octet for carbon. So these other electrons must go on the oxygen. And because it's symmetrical, what I do to one must be done to the other. So here's something I'm going to point out. When oxygen has a double bond, you make little ears on it. So that's 4 right there, which leaves me 4 valence electrons. So I'm going to put my ears on the other one, and that's when this is a double bond. So if I did this right, this should be a full octet. 2, 4, 6, 8, that's good. 2, 4, 6, 8, we covered that one. 2, 4, 6, 8, we covered that one. So this is my way of doing Lewis structures. Remember, it only goes up to 2p, but believe me, you can do a lot of compounds that go up to 2p. So next one, we're going to do a little bit different, a little bit harder one to show that these are all still within 2p, so this will work. So one, I'm going to pull these out. I have 2 carbons, I have 6 hydrogen, and 1 oxygen. So this is 2 times 4 for valence electrons. I have 6 times 1, and I have 1 oxygen, which is, we're just going to leave it with the valence electrons. So we have 8, 6, and 6. So this gives me a total of 12 and 8. This is 20 valence electrons to work with. Now we're going to do the same thing and write these out. This is not 10, this is 1 oxygen. So we have 2 times 8, 2, let's do 6 times 2 for a duet. This is an octet. And 1 times 8. We'll just keep it consistent here. So this is 16, 12, and 8. All right. So if this is right here, let's do it this way. This is 20 and this is 16. So this is 36 electrons. This is what I want to have, but I don't. So number 3 is to subtract these. So 36, subtracting 26, I have 16 valence electrons to share within this compound. The next is to make this as symmetrical as possible. This is something you may not realize, and what we're going to talk about a little later. How this, you might want to ask, why aren't the hydrogens all put together in the carbons? Sometimes how a compound is written out is exactly how it is when you put it together. So what do I mean? Well, I have a carbon here. Carbon is a central atom. Hydrogens never will be. I have another carbon here, and I have an oxygen. Why did I put these here? Because hydrogens will never be in the center. So I'm just going to plug this in. This tells me that I have 3 hydrogens attached to this carbon. I have 2 hydrogens attached to this carbon, and I have 1 hydrogen attached to this one. This is what it means when you see it separated like this. Believe me, this is what you want. You don't want these all combined. It makes it harder for you to figure out how to put it together. So I have 16 valence electrons. I am going to divide this by 2. It is going to tell me I have 8 bonds within this compound. So let's put them out. I already did 1 here. So 2. So 1, 2, 3, 4, 5, 6, 7, 8. I did 8. You guys see where I did that? I had 16. I subtracted 36 by 20. This is what I want to have with full octets or duets. These are the valence electrons I have to work with. I subtracted them. It gave me a number, and I divided those by 2 to determine how many bonds are in this compound. And 1, 2, 3, 4, 5, 6, 7, 8. So I have 8. Now I need to put on the remainder, whatever I have left. So number 5, I'm going to subtract my 20 that I have from my number that is here, 16. 16, this gives me 4 valence electrons to work with. So let's count where we have the octets. We have 2, 4, 6, 8. The central carbon has it filled. 2, 4, 6, 8. This middle carbon has it filled. That means that my lone pair have to go on the oxygen, because you can see I only have 2 and a 4. So I am missing them. When you have a bond with an oxygen that goes on this side and this side, the lone pair, you can put them you can put them like this. That's my 4. That's done. So let's count. 2, 4, 6, 8. I am done. So this is how you can put carbons together. Structures together, my Lewis structure way. It's not foolproof. There are exceptions, and it doesn't really work past 2p. But even with after or 2p, you can still use it and it gives you a better idea than just struggling. All right. So that's my quick tutorial on Lewis structures. I strongly suggest you stop here and go back to see the video I made with how to do this. But if not, we're going to get into VSEPR theory. So Lewis structure helps us get into VSEPR theory because we need to know the shape of these molecules. When we write them out flat, we really cannot see them in a three-dimensional arrangement. And none of these molecules are flat. That's not how they work. So based on with VSEPR theory, we learn how to create we put them in these shapes that allow the electrons to settle in positions that minimize repulsion and maximize attraction. So they're set in just enough way to have attractions to other compounds and minimize the repulsions between themselves on here. So the three-dimensional structure of a molecular covalent compound and polyatomic ions. There's two different types of geometry that you need to know for this lab. We have molecular geometry and we have electron geometry. Now with this, we have, excuse me, I was turning off my writing pad. Molecular geometry is normally how we define shapes of our molecules. That's the one that we look at when we define the shape. It is the attachments. I call them attachments, but they're bonds. A bond's around the central atom. Does not include lone pairs. Electron geometry is exactly what it sounds like. We count all the attachments, including the lone pairs, but they are different. If there are lone pairs on a molecule, the molecular and electron geometry will be different. If there's no lone pairs, they will be the same. So I'm going to give you guys an example, and you're going to be given a chart in order to understand how this is. And again, we're going to go even further next week on this. So here I have water. You can see it here. It's moving. You do not see the lone pairs that are on it, which you can see, which is more realistic is how it's covered here than here. But the lone pairs are there. And in this nice little orbital, you can see. It has two different geometries. When you have electron geometry, where we count the lone pairs, it has a tetrahedral. When it's a molecular, it's a bent. Now, I realize you probably have not heard of these names or these words since 10, and even then, I'm not sure who of you have covered these shapes. We're going to cover these shapes more next week. So I'm going to break this down as much as I can for this lab and then focus on more next week. By then, you definitely should have enough information to do some of these things on your own. So how did I come up with these geometries? Well, I found this chart online. I'm going to give this to you. This is not the chart I use, and I'm not going to give you this chart. I'm going to give you the one on the next slide. I don't really use this chart, but you definitely should see this because most books carry this chart, which to me is just a little bit more confusing than the one I use. A stands for the central atom. X is any atoms bonded to it. And E stands for a lone pair. So total domains is all attachments to a central atom. So if I look at water, here, water has 4 domains attached to it. I have 1, 2, 3, 4. I am including the lone pair when I'm trying to determine what the geometry is. So you count everything when you're trying to figure out where to place this in. So I have 4 domains. I'm going to go down here. Now skip all of this and go to where it says bonded and lone pairs. Water has 2 bonds and 2 lone pairs. So I'm going to go down here. I'm going to go to 2 bonds and 2 lone pairs. This now gives me my geometries. This is molecular geometry. This is my electron geometry, and sometimes they'll give you an example. So here is for my molecular shape, it is bent. And for my electron geometry, where you include the lone pairs, it's tetrahedral. So let's see if we have bent and tetrahedral. We do. This is how you read it. I use a different one. You go past the next slide, it's right here. Same thing, but it's just for me a little easier. It gets the A and the E's and the X's out of it. Electron groups is the same as domains. You count everything that's attached. We have 4, so I'm going to go down to 4. I have bonding groups. I have 2 bonds and I have 2 lone pairs. I have electron geometry of tetrahedral. I have molecular geometry of bent. Next week, we're going to get into bond and bond angles. And this one even gives you a little example of what some things look. So even though these show the electron pairs like this, it is really like this. So this is not overly difficult, but you definitely should start coming to understand these better, because we're just going to keep building upon this. And that starts with Lewis structures. So make sure you really do understand how to put Lewis structures together. Okay, so I also included another slide to give you an idea of what some of these geometries look like, molecular geometries. So here you see it as a Lewis structure. It's flat. Here it's a 180. This is considered linear. And over here I did ammonia. Now, in most cases, the lone pairs are never shown. I found one that had the lone pair so you can see it. This lone pair causes the geometry of these bonds to be pushed down because this takes up so much more room than the bonds do. And this is trigonal pyramidal. So it's more like a pyramid. Planar is flat. It tends to be flat more than what this is. So here you could see when you have it, when it's molecular, they don't count the lone pair. They don't look at it. But when you do, an electron, here it is, you can see that this would take more space and it pushes them down. Water's the same. Water has a bent geometry, which is similar to SO2, but in reality, these electron pairs actually push the bonds closer together because they take up so much more room. All right, so how do you write geometry for a molecule with more than one central atom? So I'm going to show you how to do this. You can do this with anything that's considered a central atom. This molecule actually has 3 central atoms. We have a carbon, and an oxygen. And I'm going to show you how to read these because in LabFlow, certain parts in your quiz or in the lab may ask you some of this stuff. So I picked ethanol. Ethanol is written out exactly the way it is in a structure for this one, not always. So I'm doing a generalization. Let's look at the first carbon. Let's call this carbon 1. It has 4 attachments. We don't care what the attachments are. It has 4 attachments. 1, 2, 3, 4. I have 4 attachments. So I'm going to go down to 4. I have 4 bonds and no lone pair. It's tetrahedral and tetrahedral. We go by molecular geometry for the shape. It is tetrahedral and it looks just like that. So we got that. Remember, when there's no lone pairs, the electron geometry and the molecular geometry match. But we're not done. We need to know the geometry for all central atoms in this compound. So let's go to the next one. So now we're going to look at the second carbon. And this carbon has a hydrogen attached, a carbon, a hydrogen, and an oxygen. We do not care about these lone pair on the oxygen because we're focused on this central atom. Yes, when we do a Lewis structure, we need to make sure everything has an octet. But when we're looking at geometry, if it's not on the central atom, we're really not concerned with it right now. So again, we have 4, 4, and 0. This is also a tetrahedral geometry for molecular. And then the last one has to do with the oxygen. The oxygen is a little bit different because it has lone pairs on it. But we are interested in electron groups, and that includes lone pairs. So let's count. 1, 2, 3, 4. So we go back down to 4. Now this is not going to be tetrahedral because we have lone pairs. So we've got to pick. We have bonded groups. We have 2, the hydrogen and the carbon. Then we have 2 lone pairs. So the electron geometry is tetrahedral, but my actual molecular geometry is bent. So it's going to be more like this. So this is going to help you determine geometry of a molecule that seems kind of long. Just focus on the central atom that you're looking at and count the attachments, and you'll be given a chart like this, and it will make your life much easier to understand. Lewis structures are more complex molecules. So this is exactly what very similar to the last page. Sometimes how the molecule is written is exactly how it's set up, minus lone pairs. Lone pairs are not ever written in a chemical formula. So this is where you need to understand Lewis structures, because if you do not draw and make sure compounds have octets that need octets, you're not going to write these out correctly, and everything else after that is going to be wrong. So we have this one here. We have it out. We put this here. It's exactly as it's written. The OH, this is actually an alcohol, what this means. And once you get to organic and so forth, you'll learn that. That is here. The H is with the oxygen. It's not to be on with the lone pair. That's what this is telling you. Second is ethanol, which we just drew. Sometimes you'll see it with the lone pair on the oxygen, sometimes it won't be. So just because you don't see lone pairs on molecules does not mean they don't exist. It means it's implied that you understand enough about chemistry to know that they're there. We do have exceptions to the rules. We have compounds that, some elements that do not need and will not fill an octet. Hydrogen and helium, for instance, fill a duet. But we have beryllium and boron. They do not need an octet. They are happy without octets. So beryllium has 2 valence electrons, and that means it has 2 open spots. So if another element comes in and donates an electron, it will be very happy with a total of 4 electrons around it. So beryllium hydride here is very stable, just like this. Then we have boron. Boron can have it has 3 valence electrons with it, and then it has 3 open spots. So if an electron comes in and donates one of their electrons, it will create a bond, and this is very stable with 6 electrons around it. Then we get into resonance. So Lewis structures, we're expanding more on this. Lewis structures help visualize the bonding in molecules, but there's limitations. We have some molecules that one structure is not going to justify what's actually happening there, and that's where resonance comes in. These structures differ only in the placement of multiple bonds and lone pairs, definitely not the charges. So if we look at this is carbonate ion, this is carbonate. It has 3 oxygens and double arrows. This means that all of these structures are equal. You have to show that there's a charge to this consistently. So what this is saying that this oxygen here has a double bond, but it is not any more important than this one and this one. So the double bond will move between the 3. How do you know how many structures a resonance structure tends to have? Well, oxygen tends to be one of the main, nitrogen as well does resonance, and there's a few others. But if you see something that looks very symmetrical and you can move this bond around, that's going to kind of give you an idea. So I have 3 oxygens here. I'm going to have 3 resonance structures. It's not set in stone, but it's a good way to kind of have an idea of how many structures you need to account for. This double bond needs to be on all of these oxygens in order for this to account that not one oxygen is more important than the other. They are all equal. That's what resonance means. This bonding, this energy is being shared, and what resonance means is that these bonds are not actually double bonds or single bonds. They're a little bit in between both, but this is the best way to represent it. So if we look at here, this is actually what it means, these dashes. This energy is actually shared between them, and the values are not really double bond or single, they're in between. But we don't draw this like this. We show all the structures as a representative that this energy is being delocalized between all of them. So this fancy delocalized word, it just means that all of this energy is being shared between these bonds that are very symmetrical in it. So this carbonate has 3 structures. So if you get a compound that has oxygens and they look very similar, most likely how many oxygens you have, that's how many resonance structures you're going to have. And you need to always put the charge. This is an ion. This is a polyatomic ion. If there's a charge, you have to show the charge. Here's another example of a nitrite ion. This is what I mean. You have an oxygen that has a double bond. You have one that has a single bond, but you don't, this oxygen is not any more important than this one. You can flip this and show that the double bond here and the single bond is here, and these both are equal to each other. So because I have 2 oxygens that I can move that bond around with, means I'm going to have 2 resonance structures. Electronegativity. Electronegativity is a measure of the ability of a bonded atom to attract shared electrons. So think about this as a tug of war pretty much. The stronger element's going to hold the electrons closer to it and away from the weaker one. Fluorine is the strongest electronegative atom. It's going to pull the electrons way over to it. Noble gases aren't counted here because they're pretty, I mean, there's some numbers, but they're pretty on their own. They don't like to be bothered, so we don't include them. And these numbers do not have values. They don't have units, excuse me, not values. They don't have units to them. We're going to come back to what these numbers are, but this is just an idea. Fluorine is the highest, then oxygen, and then everything else around it starts going down. So if you have to kind of do an arrow, this is the highest one. Fluorine's always going to pull the electrons more than any other element. Why does that matter? Because now when you understand Lewis structures and you draw something, you're going to need to understand how compounds share electrons, covalent compounds, and it's not always even. An element with a high electronegativity pulls shared electrons closer to it and away from the element with a lower electronegativity. So what this means is that you can see here, somebody drew this. I found this online. Fluorine has the most, oxygen is next, nitrogen, and then this means that these are almost equivalent. Yes, the numbers are slightly different, but they are almost equivalent where there's a very small tug of war going on between these electrons. So if you're given a compound, how do you know which one to make your central atom? This is how I was taught, is to look at electronegativity values. And the lowest value, not including hydrogen ever, because it can only have one bond, that's the element that's going to be in the middle 99% of the times. And if not, there's always something more going on that you should be learning in that chapter to help you know how to do that. So here I'm going to show you, this is again straight from your book. Electronegativity values given here. It's going to be the lowest value that's not hydrogen. So my phosphorus is going to be in the middle here. And then that will allow me to put this Lewis structure together. I put lone pairs on this so you can see, but this compound did not show them. So this is where you have to get used to understanding. There's lone pairs that exist. So I call these my little ears because there's a double bond. But you need to know that some of these have lone pairs. They just don't show them. So central atom tends to be the lowest in electronegativity value. So fluorine would not always be a central atom because it is the most electronegative. Technically, we'll cover that right now. Electronegativity and bond polarity. Two identical atoms share electrons completely evenly. So here we go with fluorine. Fluorine shares these. So if you look at this as a tug of war, this is a tug of war that's never going to go anywhere because they're equal in strength. So they're just going to try, but nothing's going to happen because they're exactly equal. This is a nice little color to give you an idea of what's happening here. So fluorine is the strongest. It's going to pull all the electrons away from hydrogen. The bond still exists, but what it does is it does an unbalanced here. This purple means that this is a partial positive area. This red means a partial negative area. So you can see there's a lot of red here, and that stands for that this is where a lot of electronegativity is. And when it does that, it's pulling away, leaving this area over here partially positive. So when you think of there's an imbalance. There's not a sharing here, and you can see the colors actually change. If you've ever slept in the bed with maybe your cousin or your sister, or in my case, I'm married. My husband steals all the blankets. This is exactly what it is. I am cold because he took all the blankets away, even though we're in the same bed. Now, I have my own blanket. Now I do not share. But this is exactly what it is. It's a tug of war, and this one's keeping all of it, but you're still holding onto the rope over here. This is a small letter delta. It's a small Greek letter of delta, so it's different than the triangle. But this is how we show that there's a partial positive and a partial negative here. So hydrogen has a partial positive. It's being kind of pulled, the electrons being pulled away from it. The blanket's all over here, and a partial negative, where fluorine, because it is so electronegative, is pulling everything with it. So this is what this color means. And this has no change in color because it's never going to. The tug of war is never going to go anywhere here. So that's pretty much what I'm saying here. I just summed it up. That it's pulling them closer, and to give you an idea of the introduction of the Greek small letter of delta for delta, which is representative of polarity. And again, here's a couple more. This is CO2. CO2, you can see the purple. So oxygen is the second highest electronegative atom, and it's going to pull, this is carbon. I'm going the opposite way. This is carbon. It's not as strong. It's equivalent to almost hydrogen, and oxygen is the second most electronegative. So it's pulling away in this way, in these portions, away from the center. So that's going to create a partial positive center, and the oxygens are going to create a partial negative on the ends of it, terminal ends, if you want to call it. So that's what these colors represent. This is more red, and then the purple. Hot water, on the other hand, has one oxygen and two hydrogens. So you see there's a lot of purple here. This is going to create a partial positive charge, and the oxygen is going to take most of the electron density and hold it closer to it, which is why you see the red up here. So that's what polarity means. There's an imbalance of sharing of electrons, which results in a partial positive on a portion and a partial negative on another portion. Nonpolar molecules tend to share. Well, let me explain this. If you're trying to determine if a structure is polar or non-polar, you have to look at Lewis structures. Then you have to look at certain things. This all has the end fluorine, the end atoms, they're all matching, which means that the tug of war is not really going to go anywhere because this is a pretty symmetrical atom, and all the end atoms, the terminal atoms on here, are all the same. So the values, the strength, if you want to call it, yes, they're all fluorines, but they're all pulling equally on boron. So this is not really going to go anywhere. So this is a nonpolar because what's going to happen is that these are all pulling, they're going to cancel each other out. Same as CO2. These are both pulling on the carbon, but one's pulling this way and this one's pulling in the equal strength this way, and they're going to cancel each other out and make this a nonpolar molecule. Where hydrogen doesn't, where water doesn't have that. These are not strong enough to take on oxygen, and this is going to create a polarity within the water. So if it's symmetric and all the ends of that are attached atoms, the end atoms that are attached to the central atom are all identical and no unshared pairs of electrons, meaning lone pairs, it's most likely a nonpolar, but it depends on the shape as well of these. So notice that a tetrahedral molecule, so we have here a carbon and 4 chlorines here. This, because they're all the same and they're all pulling in equal opposite directions, are going to cancel out and make this nonpolar. Molecules that are matching each other, identical, are also going to be nonpolar. So if we go back here, the attached atoms to a central atom and the arrangement of the bonds of the molecule determine if polarity occurs. So that's what we're going over here. If something's uneven right here, this is not symmetrical, and how the Lewis structure is, that's going to determine the polarity. But if something is all identical and the molecule, the shape of it allows these the strengths to cancel out, it's not going to be polar. So here's a nice little cartoon I found online. If you have something that's identical, it's not going to be polar. Nothing's going to happen here because there's not an imbalance, which means you're not going to create a partial positive and a partial negative portion of this molecule. It's polar if you have an uneven balance. So for instance, this side here will be partial negative and this side will be partial positive. Because this side's weaker, the electrons are going to go on this side. If you have a compound that has all equal end atoms, terminal atoms, and they're all pulling in equal strengths, they will cancel each other out. This is nonpolar, nothing's going to happen. If you have a compound that has even one atom that does not match, and it's more electronegative than the others, this is going to create an uneven distribution of these electrons, and it's going to cause a partial positive and a partial negative. And the side that pulls more is going to be partial negative. These are going to be partial positive. And if you have two atoms, again, if it's not balanced, all three, two atoms that are more electronegative than this one's going to be partially positive, and this one's going to be these are going to be partially negative, causing this compound to be polar. Why does this matter? Well, we'll get into that right now. If you wanted to go even further to understand about bonds, this is where these values come in. This is the difference in electronegativity. So you would take the 4, and you have a hydrogen, you would take the 2.1, subtract this, and it's going to give you a value, and then you can compare it to a chart, and that's going to tell you where this bond is, whether it's polar, ionic, or a nonpolar. It's going to give you an idea, and you do that for every bond. This just shows you 2 items, but if you had more bonds, you would count every single bond individually to determine what you're dealing with. So here, we plugged it in, and you can see there's values with this. Now you can take these values and you can look on a chart. Now the weird thing is when you look on charts online, these values, these numbers, they don't all match up. They're like 1 off or 1/10 off and so forth, but they give you an idea. So for instance, if you look at 1.9, This is ionic. So it's saying that it's showing that it's been transferred over. Sorry here. So even though this is covalent, it's very, very close. Now I said now none of these, I found this one online. So this one doesn't match what's been given in your book. But this is showing more ionic character than covalent. And it's going to show that most of it's been transferred over most likely. But in this case, H is a nonmetal, fluorine's a nonmetal, and they're sharing, but it's pretty close to being what is ionic. Here, polar is between. If something's more closer on this side, it's very polar. And if the number is closer to 0.5, it is slightly polar, more going towards nonpolar. And then everything is in a degree in between. So if you look here, I keep doing that. You have 0.4 here. So 0.4 falls into the nonpolar, and it's close to this, but it's really got nonpolar behavior with it of sharing of electrons. So that's what this means, that HI is the least polar, so it's considered nonpolar, and these are in between. And then you have on this one, at the top of the scale is HF. This one has the most ionic character out of all of these based on this number that you can check this chart. Like I said, this chart's fluid. Most of these charts, these numbers, they're all over the place. They're close, but there's not one set number, but it gives you an idea of what you would be dealing with. Again, I just found this online and I'm giving it to you so you can see. Well, if we were in person, you would be given something like this and you would have to show me, you would have to draw these deltas with where the polarity is if they were polar molecules. This has lone pairs on it. You don't see them here. Nonpolars, there's no lone pairs ever on a carbon. There's a lone pair here, there's a lone pair here, but this is equal, so there's nothing going on with that one. Again, I'm giving you a full electronegativity chart so you can see what the values are for these. Dipole moment. A polar covalent bonds are dipoles. So this is a separation of charge. So for instance, CO2 causes a charge here, a separation, because this is pulling this way and this is pulling this way. This is the introduction of these fancy little arrows. What it starts with is you place the end of it is at the atom that is the partial positive, and the arrow tip goes towards the electronegative portion. So when I look at this, this tells me that this electron density is being pulled from the carbon onto the oxygen, and in the same way this way. Now, this is symmetrical. Because it's symmetrical, these cancel out. But if it's not, you would actually have to draw a bigger arrow in magnitude and direction showing me where the dipole moment exists for these compounds. So you can see hydrogen is here, the tip is here. So this means that this electron density is going this way. So you would draw these nice little deltas with the positives and negatives, but you would also do an overall of a dipole moment showing what is actually happening with this molecule. And based on the magnitude and direction, how big that separation of charge is between these molecules. Basically, the electrons are being pulled one way. It's going to leave a nice little separation here in this electron density. This, you can't see this one very well, but this is the overall. You can see that the hydrogen electron density is going towards the oxygen. Same thing with this one. So you have two arrows here, but then you have a bigger arrow, which I wish they didn't have in this color, or I could find a better picture of this to show that you have a overall molecular dipole that's going straight to the oxygen. So it's being pulled from this section towards the oxygen, and this is the overall dipole of this, which is a separation of charge. I just put these together. I found this online so you can also see what I'm talking about. This is the arrow I'm talking about. There is an overall molecular dipole moment because this oxygen is pulling so much of the electron density. There's a nice little separation that exists between these. The purple means that there is an overall dipole moment on these, and you can see what net dipole means compared to no dipole. This cancels out. This does not. This does not. This cancels out. So even though these have polar bonds, they can actually be nonpolar molecules because those get canceled out if they're based on the arrangement of that molecule and if all the terminal atoms are all the same. All right, so here's the fun part. This is your lab. Yes, I'm giving you a lot of answers to portions of it. Because we haven't covered what basically these 3D arrangements more, I really don't think that you guys would understand doing this portion of it. You probably could, but next week we're going to cover it more, and then after that, I'm not giving answers to anything. So you are still responsible for answering for these group T compounds, the rest of this information here. Sarek, number is all the attachments, including lone pairs on something. So this is why I'm strongly suggesting draw these Lewis structures out. Don't go online. Draw them out so you can actually see what's happening. You will have to answer for electron geometry, number of bonding electron groups, number of lone pairs, and molecular geometry. Now, go one step further. Even though I'm giving you guys the answers, you will need to understand how to do this. This will come back in and can hurt your grade later on, even if it's not now. We're only going to expound on this. Plus, when you get to 24B, this does not go away, and you will not have time to refresh and learn what you didn't learn because you got it off on the internet. Not most of you guys. Most of you guys are doing pretty good, but I know that when students, including myself, don't want to do things, it's really easy to go online and see. But if you don't learn the concepts, you're not helping yourselves. So I've given you the answers. Once you've done all this, look at what's being asked here so you can figure out why something's not polar or why it is polar, to understand better and visualize what's actually happening with these and how come some dipoles cancel out and others do not. Same thing for group W compounds. I'm giving you some of the information. I would suggest strongly that you still draw all of these compounds out. If you draw all these compounds out and you follow my way or with book, you will do very well with this. This is not stuff you tend to forget. It's really something that you would hold on to. And then you have resonance structures. They're same. I'm giving you some information. You will have to do the group U compounds here. And the last portion, this is where polarity comes in. This is actually a really cool lab when you can do it in person, but unfortunately we can't, and I do not like these drawings that Love Flow gives. So I'm going to help you out with some of these, and then you will have to do the rest of them. So you're going to determine if polarity with compounds also goes into polarity with solvents. For instance, water is a polar solvent. Why? Because I've showed you why. The imbalance of the electrons within the hydrogens and the oxygen causes a partial positive and a partial negative. That creates a solvent that is now polar as well. So when we look at these, we have water that's polar and oil that's nonpolar. If we go even further, this is a statement that really explains polar and nonpolar very well if you have to compare stuff. Like dissolves like. This means that if you have a polar solvent and you put something in it that's, you want to find out if it's polar or not, if it dissolves in that solvent, it is whatever that solvent is. So if I have a polar solvent and I put sodium chloride in it, and sodium chloride, which is salt, dissolves in the water, and I do not see two layers, separate layers, like I did here, it is whatever that is. So it is polar. If I put something in there, as in what you see here, or salad dressing, no matter how much I shake these up, there will always be eventually a second layer. There will always be a distinction of two layers because one is polar and the other is not. And they will never want to be together no matter how much I mix them together. They will eventually separate out. Nonpolar solvents dissolve nonpolar compounds. Same thing. If I have oil and I put sodium chloride in it, it's not going to dissolve it. It's not going to do anything. It's going to want to create a second layer. So if I put carbon tetrachloride in with an oil, it's going to mix with it enough that you're not going to see a second layer. So what happens here overall, if something dissolves in that polar solvent or nonpolar solvent, there is one layer. If you see two layers, it didn't do anything. They're separating out. So when you see salad dressing, that's what's happening. One's polar, one's not. Here's a good idea of it. You pour the oil into the water. You can very well see two strong layers. That's what this blank is supposed to look like. That's why I say these drawings are horrible. But they get the job done. I shouldn't be that hard on them. That's what this means. Water sits at the bottom because it's denser than oil. It's heavier. This is why when there's oil spills in the ocean, it's a big deal because the oil just sits on the surface and oxygen and other things cannot interact with the water underneath. It'll just sit and pretty much suffocate and put a nice little blanket there because oil is not as dense as water. So there's some fancy terms that really explain this. This is hydrophobic, means does not like water, and hydrophilic, loves water. So anything that's nonpolar is hydrophobic, and anything that loves water is hydrophilic. That's what these words mean. So this is your blank, and all you're pretty much going to do, because you see two distinct layers, is you're going to compare your blank with each of these test tubes. You're going to compare this to this and see what the changes are, see where the compound went into, because it'll stay away from the other one. Take this and compare with this one, take this and compare with this one, take this and compare with this one. So I did a couple of these to help you so you can see what's going on. So you have elemental sulfur, which is an octagon. It's bright, it's a non-metal, and it's a powder. And if you place this into you place it into your oil and water mixture, it's going to go into one compound and try to stay away from the other. And that's how you can determine if this is polar or non-polar. So you can see where the color change occurs. It didn't change down here. Excuse me, it changed up here. So that means that this is non-polar because oil is a non-polar liquid. Now, these little parts here, what happens is eventually when you deal with solutions and solvents is they hit max of dissolving. They can no longer dissolve anymore. And that's probably what happened here is that it had hit the max of what it can dissolve. And it ended up being heavier than what it can hold into the oil. And it just dropped into the water. Even though it doesn't want to be there, it's just heavier. So it didn't sit into the oil very well. That's all this means. Second one, sodium chloride. If you guys have ever boiled water for mac and cheese, then you kind of have an idea of what's going on here. An ionic compound, most ionic compounds, if not all, are polar. They will dissolve in water. This is salt water, and you cannot see the crystals. So you see there is no change between the blank and the sodium chloride in the water. I'm sorry, my mind went blank for a minute. And you can see why. The ions will break apart, and the water that is partial positive will be attracted to the negative, the chlorine, and the part that's partial positive, the water that is partial negative will be attracted to that part, and it will block it. It will hydrate these ions so that they can't get back together. I'm not going to tell you this one, but it should be pretty apparent. I found a picture of iodine, and you can see where it's sitting. Same thing happens. These are probably just heavy. That's why they're coming down. But you can see that's sort of trying to match what it is. Here's your blank. You can compare it, and you can see where this color stays in and where it stays out of. Here's some summarizations of what I've covered in this lab. If there is a carbon in the molecule, it tends to be the central atom. Oxygen, sulfur, phosphorus, carbon, and nitrogen can have double bonds. There are more, but this is just a generalization here, strictly generalization. Oxygen, carbon, and nitrogen can have double bonds. Again, just a generalization. Carbon should never have a lone pair on it. Yes, but you'd have to go into many other chemistry classes to get to that point. So as of right now, cannot have it, forbidden. If oxygen has a single bond, it tends to have 6 electrons around it. If oxygen has a double bond, it tends to have 4 electrons around it. Think about ears. Hydrogen never has more than one bond. It's a terminal atom. That just means an end. Bonds on a molecule can be polar, and the molecule can still be non-polar. Bonds will cancel out the polarity. So this is a summarization of this lab. Yes, it's a little longer, but I hope that what I covered gives you a better understanding of this chapter because we're definitely going to build upon it with next chapter. And that is it. So thank you.